So in this video, we are going to specifically define what we mean by a minimum spanning tree compared to just a regular spanning tree, which we covered in the previous video. Now, a minimum spanning tree is a specific type of spanning tree that still connects all the vertices together, but with the minimal total weighting for the edges. So we want the weight of the edges we select on our spanning tree to add up to the smallest possible number. We're going to see the relevance of this in the next video, but this is what we mean when we talk about a minimal spanning tree as compared, or a minimum spanning tree as compared to a regular spanning tree. They both have to connect all the vertices together, but a minimum spanning tree will give us the minimum total weighting for the edges. Now, there's an algorithm that we can use to find this to make it sort of systematic for us. Some people, if you're watching this, you may have your own method for drawing up a minimum spanning tree, but essentially to do this, we're basically going to systematically work through. But we typically start on a particular vertex and we look at the edges around it and choose the one with the lowest weight. So that's our first step. Now, if they have the same weight, if it's, for example, two edges, they have the same weight, it doesn't matter which one we pick, but we now will have two vertices and one edge. From there, basically, we look at the vertices that we have and inspect an edge with the lowest weight that is near it. And we ignore the ones that would connect the tree back to itself. Because remember, we don't want any loops or cycles. Then we'll have three vertices and two edges, and then we keep repeating our step until we have connected all of the vertices. Now, looking at this particular example, it's best just to jump straight in to sort of give you a feel for how we would do something like this. But if we look at this particular example, we are going to apply Prim's algorithm to find the minimum spanning tree for the network graph on the right. Then we're going to calculate the length of the minimum spanning tree. So what I like to do when I choose a vertex, I want to choose one close to an edge with the smallest weight. Because if an edge has the smallest weight out of all of the edges here, it's definitely going to lie on the minimum spanning tree. So let's just go with the alphabet. Let's start at vertex A here. And I'm going to draw along this edge of 2, which is the smallest edge here, as well as this one. So I'm going to start here and I'm going to, let's go over it in red. I'm going to connect these two vertices up, okay? So I have my first edge connected. Now, when we look from here, I just want to see what I can connect to either A or B in order to start to drop my minimum spanning tree. So I'm going to inspect all of the edges around this. From B, I can go to C. From B, I can go to D. From A, I can go to D. Or from A, I can go to F. Now, the smallest possible one I can take is going to be this one over here. So from A to D, I'm going to draw my line to connect this one to this one. Remember, I don't need to make any loops or cycles because it's a tree. I just want to make my way around this diagram so that all of the vertices are connected. Now, once I get to here, I'm going to inspect my vertices again. So I have A, B, and D that are connected so far, and I want to make my way around to this part of my network diagram. So I'm going to either pick A, B, or D, the edges connecting those, and see which one is the smallest possible edge. Now, I can once again connect B to C. There's no point connecting B to D again because D is already connected to A, and that would make a cycle. Or I can go A to F, or I can go D to F, or D to C. But we can see that this edge connecting D to C is the smallest one here. So I'm going to connect the one with the smallest weight. And as we go through this, you are going to get a lot of practice sort of doing this in a systematic way. Now that we consider all of the ones that are connected, it's most likely that I'm going to pick something on this end because I want to make my way to connecting E and F as well. Now, I can either go from C down to E, I can go from D down to F, or D to E. I'm obviously going to pick C to E because 5 is the smallest number of all of these edges. It's the smallest weight. So I'm connecting C to E, And then I just want to connect to F. So there's a bunch of different ways I can go to F. I can either go E to F, D to F, or A to F, and I'm going to pick the one with the smallest weight. So I'm going to go from E to F over here. Now I have my minimum spanning tree. Just to double check, let's see how many vertices we have. 1, 2, 3, 4, 5, 6 vertices, and I have 1, 2, 3, 4, 5 edges. So it basically marries up with that definition for a spanning tree we gave in the previous video. And it's a minimum spanning tree because it has the smallest possible sum that this can add to. And remember, it doesn't matter that we don't have any cycles or loops because we don't need to connect this in a circular kind of way. We just want to make sure that somewhere each of these vertices is connected to another via an edge, okay? Now, I'm going to show you as well, just with how you want to lay out your working out. Sometimes you don't get the correct spanning tree here, but to show your working out, you should write that with your length, you should tell the marker how you are finding this length. Typically in the Australian HSC, which is where I teach from, we basically give minimum spanning trees. They're typically 2 to 3 mark questions. So if anything has gone wrong with your spanning tree, you should show your working out so that you can get an extra mark here or there. But this is how we're going to lay out our working out. We're going to go length equals 2 plus 5 plus 3 plus 5 plus 2. That maybe took 5 to 10 seconds, but it covers us in case we've made a mistake here and we get the wrong answer, but we still show that how we've gotten to that. So it takes a little bit extra time, but it may get you a mark in the long run, which I think is worth it. And here, this is a length of 17. Now, they haven't given us any units for these weights. They haven't given us meters or time, whatever, but so I'll just write 17 units. But 17 would also be accepted as well. Now, looking at example 2, we're going to do the exact same thing, right? We're picking a starting vertex, then we're basically connecting to another vertex to make our first edge, and then we're systematically working through with Prim's algorithm. Now, I'm going to pick this vertex where the tank is, and I can see that if I connect this to this one over here, I get my smallest possible edge, right? We want to start with the smallest possible edge because we know for a fact it will be on our minimum spanning tree. Also, just with this question, it's asking for the minimum length of pipe needed because we have to connect the outlets from the tank to each other. We have to connect the tank to each of the outlets, okay? And everything just has to be connected. So we've done this. Now, from my tank and outlet C, I want to pick what the smallest edge around will be, or where the smallest connection can be made. Now, I can see that 5 is the smallest number, so I'm going to connect the tank to outlet D. Now, I want to connect outlet B as well up here. Now, I can see that it has a degree of 3, so there are 3 different edges that connect to it. I'm not going to pick 11. I'm not going to pick 13. I want to pick the smallest possible one. So I'm going to connect this one that has a weight of 6. Now I want to work my way back to this left-hand side of the diagram. And it doesn't matter which one of these you want to do first, but we're just picking from all of these vertices that we have selected what an edge close to it of the smallest possible weight will be. And we can clearly see that of all of these, 11, 13, 11, 9, 8, 8 is the smallest one. So I'm going to connect the tank to outlet E. And I'm basically just working my way around it, okay? From here, I want to look all of my vertices that are selected. What is the smallest possible weighted edge that will connect me to another vertex that hasn't yet been selected? I still need to connect to outlet A, outlet G, or outlet F. But I'm going to examine all the edges that connect to my current vertices. So from this one, I can either go 11, I can go 10, or I can go 7. I'm going to pick 7. That's my smallest possible one. Now, from here, I still need to connect outlet A and outlet G. And I want to pick the smallest possible edge. Now, I have 11 here, I have 12, I have 10. I can't connect the 6 yet because neither of these vertices have been connected to our minimum spanning tree. So using our Prim's algorithm, the current one that we have, the smallest possible weighted edge is 10 from the ones that are currently connected. And then now to connect outlet A, I can either connect it to outlet B with a weight of 13, this one with a weight of 11, this with a weight of 6, or this with a weight of 12. I'm going to pick the one with a weight of 6. Now, let me just go back a couple of steps. Some of you, when doing this, you may just see it and want to say, well, okay, I can already see 6 as the smallest possible edge, so I'm just going to connect that here. And then the last one, the smallest one out of 13, 11, 10, and 12 is going to be 10. So I can connect this here. You can absolutely do it that way as well. Some people have different methods for doing their minimum spanning trees, but I'm just teaching you how we would do this in a really systematic way using our Prim's algorithm that we discussed earlier. So now that we have all of these numbers, we are going to show our working out. So the minimum length, I'm going to plus everything together. So I'm going to do 7 plus 10 plus 6 plus 8 plus 5 plus 2 plus 6. So I have all of these here, and looking at all of them, adding them up, and in an exam, you may as well use your calculator, right? There's a reason we give you calculators, just to make sure. But we should get, adding these all together, we have 7 plus 10 plus 6 plus 8 plus 5 plus 2 plus 6. That gives us a length of 44. So our minimum length is 44, and this time they have given us a unit in the question, distances in meters. So we are going to write 44 meters. So this is how we can draw up our minimum spanning tree, and we can do it in a really systematic way using Prim's algorithm. If some of you are doing these and you just see the answer and you're maybe a visual person, you can really just pick it off by drawing it in bits. You can do it that way as well. But hopefully this video gives you a sense of how to do this in a more systematic way to draw your minimum spanning tree and connecting all of the different vertices together. But that brings us to the end of the video. Thank you so much for watching, and I'll see you next time.